let's say that you own a business near a beach and you want to predict what business is going to be like on different days. And so you might think that perhaps the temperature is one contributing factor to how many people show up to the beach. So on some days, you got a bunch of people on the beach, and on other days, not so much. So let's look at two different scenarios. At one particular point in time, it's a sunny day, it's a great day. And on that day, it could be, let's say, 90 degrees. A lot of people are at the beach. On another day, it could be that it's just cloudy, stormy, and all that, and people don't show up to the beach. So at this time, it might be 60 degrees. Maybe somebody still shows up to the beach to search for treasure or something, but it's not as popular. So what you could do as the business owner is you could collect data from the past to help you make predictions about what business is going to be like in the future. So what we'll do is we'll make a chart here of temperature and visitors. On one day, it could be 90 degrees, and the number of visitors could be 400 visitors. And in another case, it could be 60 degrees, and you only got 100 visitors. Maybe you take some more data at other temperatures too, like on one particular day, it's 85 degrees, you count the visitors, and it's 350 visitors. But then on another day, it could be 70. And you only count 200 visitors. Each of these represents one day. Okay, so that's day 1, day 2, day 3, and day 4. Your sample size here is n equals 4. All right, you have 4 data pairs. Now these are called data pairs because you have 2 variables and you're trying to see if there's a relationship between the 2. Okay, now I could put these variables into a fishbone diagram. Which variable is the cue here, the thing that you're observing and trying to explain? The effect that you're trying to explain is the number of visitors. Why is it varying? Now, you might also think about whether that makes it the independent variable in the situation or a dependent variable. What would you say it's more similar to? An independent variable or a dependent variable? Like, for example, do the number of visitors depend on the temperature, or does the temperature depend on the visitors? Let's put it this way. If I was to give a hypothetical, does Mother Nature look down on the situation and say, hey, there's a lot of visitors on the beach there, let's raise the temperature for them? Is that how it goes? That's not how it goes, right? It's actually the other way around. The people, they see what the temperature is like, and then they run to the beach. Yeah, they're coming to the beach because they see how nice it is out. So let's get there, okay? So which one's really the dependent? The temperature or the visitors? Yeah, the visitors is called the dependent variable here. They respond to the temperature. Now, when that's the case, you want to make the visitors the y variable, the vertical variable. So this will be the y, and that makes our temperature the x. Now, temperature is one possible explanation for why people might show up to the beach. It is one contributing factor. Should we assume that temperature is the only factor in the situation and it completely predicts why people show up to the beach? No, because there could be other things that people show up to the beach for. What are some other possible causes for people showing up to the beach besides temperature? The what? Yeah, okay, maybe they're surfers. Sometimes those crazy surfers go out, even though it's super cold, they may still be out there in their wetsuits because they love the sport so much. That's a great example. Waves could bring people to the beach. So maybe, let's say sports Sports and waves. Okay, what else? Oh yeah, it's a perfect one. Events at the beach, concerts at the beach. How about just searching for treasure with one of those metal detectors or something? And could there be other explanations that I didn't list? There could be other explanations too. So the point is that we can't necessarily assume that this graph tells the whole story. Temperature could be one contributing factor for why people show up to the beach, but it's not the only one. So I'll ask you this. This is an important question. Is this type of situation a true scientific experiment, do you think? Or is it not quite? I'll give you an example of a scientific experiment. A long time ago, I mentioned that you could do an experiment on salt water, where you could look at the ocean on a cold day and see how the ocean was liquid, but a nearby freshwater pond was frozen at the same temperature. And we said that you could investigate the effect that salt has on the freezing of water. However, we also said that in the wider world, there were many different proposed causes which were logical that might affect the state of the water. We said that it might be the difference in salt content that was causing the fresh water to freeze before the ocean, or it might be the difference in the size of the body of water. It might be that it was a difference in the boat traffic, and it might be that there was a difference in the wind and waves. All these possibilities. And I said that it was like too complicated of a situation for somebody to just look at this and determine what the true cause is. So you had to do an experiment where you isolate the variables. And what you do here is you make sure that it's not the size of the body of water that's causing the change, because you eliminate that when you do a scientific experiment, making the two samples the same size. Also, it's not the boat traffic, because there's no boats in the freezer. And also, it's not the wind and waves, because there's none of those in the freezer either. This was an example of a true scientific experiment where every single confounding variable has been eliminated from the situation, leaving us with only two variables, the independent and the dependent. So, is this a true scientific experiment, what the business owner had done here? They're doing some kind of science, I'll put it that way. However, in statistics, this is actually called an observational study. Some observational studies have been termed like a natural experiment. But let me explain why it's not as rigorous of an experiment as the saltwater example. Has the person really eliminated these contributing, confounding factors? What do you think? No, they didn't say anything about those. Okay, they didn't say anything about sports, they didn't say anything about events, they didn't say about searching for treasure, and they didn't say what day of the week it was. You think people show up more often on weekends than weekdays to the beach? I'll bet. They don't have control in the situation. Okay, it's not a controlled experiment. Do they have control over what the temperature is? No, all they can do is just select days where it happens to be different temperatures, and that's all they can do. They don't have the ability to set the temperature like the person who did the saltwater experiment could set the amount of salt. So this is an observational study. Either way, even though this is an observational study, it could still have some statistical and scientific merit here. We could still find association between the variables and a thing called correlation. But what about causation? So when you have a scientific experiment, like with the salt water, it is said here that you can show very strong evidence for causation. So if you increase the salt in the sample and the freezing point changes when you do that, you're showing evidence of causation. Yes, it's possible that maybe there was some magical other factor involved, like a fairy, but you've controlled every possible confounding factor that you can think of. So we have high confidence in causation for this situation. Okay, but if we're talking about this situation, we can investigate association and correlation, but not causation, because we have not taken enough steps to eliminate the other confounding variables in the situation. All right, so let's now plot this on Desmos. Okay, so I'm gonna open up a Desmos window and then copy this data table to Desmos. All right, in order to add your data to Desmos, click plus in the upper left, then click table to add a table. You just want to enter the values exactly as they appear in your chart. All right, now that we have the data entered, we can click the magnifying glass in the lower left in order to zoom to the data. Okay, so there's my data. And I'm going to do now what's called linear regression. So doing regression is made very easy in Desmos. Type in a line equation, but you can't type it in just like y equals mx plus b. This is the most common point of confusion that people run into. They're not sure why it's not working. So one of the things is you have to put ones after your x's and y's, because our table has x1 and y1. You can have more than one data set in Desmos, so they try to attach a number to each. So let's do y1, x1. You also have to use a tilde instead of an equals. Now it just so happens that the data that I had picked has perfect linear correlation. What that means is all the points that I selected are on the line, and you see that the R value is 1. That doesn't usually happen with collected data. Usually there's going to be some variation. So let's take a look at what the R value would be if there was more variation. I'll just come up with some other hypothetical data sets. Let's say you might have it be where, like, okay, on a hot day, like 110 or something, that's an unusually hot day. You might have it be where not that many people want to be at the beach. If it was 90, you might get even more people at the beach. And if it was 80, you'd still get a lot of people at the beach, maybe 350. And then if it was like 50, then hardly anybody come to the beach. Let's zoom to that data. Okay, so that's something that could be a little more realistic. Let's see what the correlation is if we do linear regression on that. Now, Desmos is going to find the statistically best fit line that goes through the middle of the data, trying to minimize the differences between the points and your line. So you want some of your points above the line, some of them below the line. It just goes through the middle. Here we see the correlation is down to just 0.75. So 1 is perfect correlation. 0.75 is still correlation, but it would be more like considered moderate or weak even. The trend is up, but the points aren't on the line. Then you might have something where your data is a little more all over the place. Like, let's say you've got 100 goes with 20, and 90 goes with 80, 80 goes with 10, and 70 goes with 60 or something. We see here that the data doesn't seem very linear at all, like a line wouldn't even really be appropriate for this situation. What this shows is that the X has no bearing on the Y, probably. They don't even have an association or a correlation. So when we do the investigation here, we see an R value that is close to 0. So 0.19 here is very small correlation. And it's said that you usually got to have about like 0.68 or so to be significant. And this is quite a bit below that. So it just shows that a line is not appropriate for this situation. And there's basically no association, no correlation between the values. They just kind of do their own thing and they don't respond to each other. So going back to my data here, for an R value of 1, what we see is that there is perfect correlation between temperature X and visitors. There's several statements you could make about that. So one of the statements you could make is that because it's a positive correlation, you'd say that as X increases, what happens to Y? Does it increase as well? Does it stay the same, or does it go down? How does it respond to the X? When the temperature goes up, do the visitors go up? As X increases, Y increases also. Now, you have to be able to put this statement into the context of the situation and the context of the data, though. All right, so with that, you just want to reference the units that were involved and just make your statement in terms of that. So X stood for the temperature, so as the temperature increases, the visitors increase also. Now, could we have negative correlation? Yes. If it was the case that we had a downward slope like this, then the negative one indicates that you have perfect negative correlation. And this would show that as the X increases, the Y decreases. But we didn't have that, of course.